That's just the lab. You also have.
All right, got the first question up on the board. Look at these three compounds. Try to identify which one of these you think has the highest boiling point. Feel free to talk to your neighbors. Figure out which one of these you think you'd have to heat up the most to boil. Those are for supplemental instruction, so they need one before they leave, but it's not immediate. All right, 20 more seconds to submit your answer. Got 22 responses, 23. Speak now, forever hold your peace. All right, gonna go ahead and close out. Wrong button. So let's see what our responses are. All over the place. So let's start with, we're trying to solve this problem. What pieces of information might we need that not everyone in this class has? What are the squiggly lines? Yeah. Okay. Squiggly lines are very important in chemistry. So we're going to spend a bit of time in class today making sure that by the end of class everyone knows what the squiggly lines mean. So I'm going to call that deciphering line structures. So line structures, if you ever see chemicals out in the public, you're not going to see carbon, 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 carbon. You're going to see it simplified down, boiled down into a structure that looks like this. So we're going to make sure that you can identify that. Is anyone here thinking about going to med school? Raise your hand high. Okay, or some sort of, do you need Orgo? Does everyone need Orgo 1 and 2? Yeah. Maybe a few people in here who decided they won't use that, but this is the basic language of organic chemistry, is looking at a structure, this carbon base, and trying to figure out what it means. So we're going to make sure you have those skills in this class. You're going to practice a lot. We should be able to answer this question once we have that additional piece of information. I will say that all of last week I didn't have anyone come to office hours. So either that means that everyone is feeling like they're nailing it right now, this is all review, they're good, or the office hour times don't work, or you guys are scared of me. And I'm not sure which it is. There's a combination maybe of some of those three. So I really hope it's not the last one. My job is to help you succeed. If you don't believe me, try coming to office hours once, and if you feel terrified, then don't come back. Use some other resources. But that's why I did a doodle poll, is to figure out when might be the most likely time that I could be available to help you. If those times don't work and I have 0 people at office hours again tomorrow, I'm going to have to change the office hours, so I'll have to do another poll. If you did reply that those hours would work for you, it's tomorrow 3 to 4:30 p.m. And then my other office hours are Friday 12:30 to 2. This Friday I'm out of town, and so I will not be here for the Friday office hours. But I will be around most of the day tomorrow if you wanted to try to meet with me, or if you have specific questions, I can usually answer over email or in Blackboard discussions. Or you have office hours, Humindra has office hours, and the supplemental instruction. I know last week we had 2 people come on Tuesday, 6 to 7 p.m., and 10 people come on Wednesday right before class. So there's a lot of additional time to go and be like, look, I think I realize that I'm not as good at this as I should be, this specific skill. Can we work on it? And we can work on those skills and get you strong enough so that you will not worry about passing this class, and you will be worried about, can I get that A or B? That's the border I want you to think about. Not if you can keep up with the basics in class. Okay. So this we're going to come back to in a second. But if we look at what the actual numeric values are, we see that while all three of these molecules have the same weight, meaning that if you weigh all the protons, neutrons, I guess and electrons, they don't really weigh much, that all of them have about the same mass for every single molecule. But do they have different boiling points? So a lot of times you can say in order to get free from the liquid, you need enough speed in order to overcome the intermolecular forces. But that's not enough to explain, the weight is not enough to explain having enough speed. All of them have the same weight, so if you give them the same amount of energy, they move in the same speed. But some of those aren't able to overcome those intermolecular forces and go out. So we're going to spend a bit more time today kind of going back over what the different types of intermolecular forces are, how to identify where they are. So hopefully by the end of today's class, you are solid in the idea of if you have a pure sample, a pure liquid, what's going on in there. This was kind of the end of your POGL activity 27, that if you had taken that and kept going beyond what we did in class, you'd get to practice and go back and look at some of the information in those tables. And so I just picked 3 of the molecules, and they're shown in different format here. So by the end of today's class, I want every student to be able to decode the chemical line structures that we just showed. And then once you have that, it doesn't matter which way I show you a molecule. I want you to be able to compare and contrast the relative strength of various intermolecular forces. We're also going to use that to predict what the intermolecular forces are in every single molecule, and then from that predict the relative boiling points of them, which is kind of what that first slide was asking you to do. Since many of you are interested in careers in science and medicine, I've developed a seminar series where we bring in people who are in those fields. They come and talk to y'all for 5 or 10 minutes, 2 different people. They talk to you for 5 or 10 minutes each and say, here's how I got to where I am. I thought I was going to do this, and then this happened in my life, and so I had to go to the Army, and then I ended up going back to school, and then I got my degrees, and then I got this internship, and whatever the pathways are and the hurdles that they had, we're bringing these people in to talk to you about their career paths. I think a lot of times it's easy to look at people in a position like a doctor or a researcher or something like that and then like, wow, they must be smart, they got right there. But that's almost never true. So this seminar series is called Friends of Science and Medicine. It's basically bringing people in that can be interesting to hear from, and we have them talk for 5 or 10 minutes about their career path, and then we have like an hour where you just get to ask some questions. Anything you want. Think of it as like coffee with friends, but they're like really successful people. So our first one is Wednesday the 12th of February. That's a week from this Wednesday. It is during the time the supplemental instruction normally is, so we're going to have to figure out what to do with that. I didn't realize I double booked, but I did. We know that it's going to be a long night, and actually, since I'm the one in charge of the seminar series, I got to pick the time right before our class. And because I know you're going to be here for a while, I was able to convince them to give you food. So there's going to be food. I can't say it's going to be amazing, maybe pizza or sandwiches or pasta, something like that. But if you come at 4:30, it's going to be in Physics 101. Physics is that tan building right there. In the bottom right corner is Physics 101. So come, show up, listen to what people do, how they got there, ask them questions. We try to get a representative swath of diversity from different backgrounds, whether that be from families that are first generation or racially underrepresented in different communities, or people live in the military, a lot of different pathways that people have taken to get to where they are. So we have Dr. Lanita White, who is a pharmacist who for a stint ran the 12th Street Clinic for UAMS. And we have Dr. Michael Bauer, who uses big data to figure out how to fight cancer. So he's a bioinformatician? I don't know. Uses bioinformatics. So I sent an announcement out about that this afternoon as well. That link is really important. You go fill out and say if you're going to go or not, RSVP, because that tells us how much food we need to buy. And it also puts you onto a platform called Handshake. Is anyone on Handshake yet? So it's a platform where you can have the university connect you with potential employers in the area or graduate schools. So it's a really good resource and network to be plugged into. So when you RSVP, you will have to fill that out, like to create an account. But it's going to be for your benefit kind of moving forward for career stuff. All right. I want you to look at this molecule and figure out how many carbons, hydrogens, oxygens, and nitrogens there are. I want you to put in 4 digits and hit send. Each one of those digits is going to be representative, so if there's 0 carbons, put 0 for the first digit. If there's 2 hydrogens, put a 2, 1 oxygen, 1 nitrogen, do 1, 1, and hit send. So go ahead and take a stab at it. Talk to the people at your table, see if anyone has an idea of how to look at these line structures and figure that out. And once you hit submit, then we'll kind of walk through the entire process. Any ideas how to decode this structure?
I've never seen it before, but I overheard people talking about like members right now, like some guys bonded to a carbon molecule.
Okay, so there's potentially carbon atoms, hydrogen, oxygen, nitrogen. So maybe if we didn't know, if your life depended on it, how could you answer this question?
Let's say there's at least 1 oxygen and 1 hydrogen.
Okay. But what's the first thing we do? If you were like in one of these like escape rooms, how would you figure out this? And there weren't any rules.
If I had no idea,
Yeah.
you mean like look it up?
Yeah. So that's the starting point. So you can look it up and then kind of back it out if you want.
All right.
All right, 15 more seconds. We're taking a guess here. I'm not judging you right or wrong. I just want you to have a foundation to start and kind of look at these.
That's what?
It's C3H8. Just one.
All right, go ahead and submit an answer. 4 numbers in a row. Hit send, please. Okay, we have lots and lots of different responses. Let's see if there's one that stands out as... We have one that has 3, so that's good, that's higher. Okay, so a line structure. Chemists, like most people, are lazy. So we try not to draw something if we don't have to. So what you're going to see here is a summary of everything you learned in Gen Chem 1, put into a structure. Simplified as much as possible. How many bonds does carbon always have? 4. So that is the foundation for these drawings. So everywhere a line starts, changes directions, or stops, is a carbon. Us organic chemists, my PhD is in organic chemistry, we rule the world. So carbon is the center of everything. So that's why these structures always have carbon as the implied atom. So how many carbon atoms are shown in this structure? Is it 3 or 4?
3.
Line starts, changes direction, stops, so that's 3. The question is there one here at the top? Nope, because there's something else written there. If there's anything besides carbon, we have to put it in, with one exception. What is the other most common element that you're going to see on every single structure that you've looked at for the most part up until now?
Hydrogen.
Hydrogen. So we're going to get lazy. We're going to say, well, we know carbon has 4 bonds, and most of the time it's the hydrogen, so we're not even going to show them. We're just going to be simple. So if we look at the far left carbon in this structure, how many bonds are shown to the bottom left carbon?
1.
There's only 1 right now, so I'm going to draw in our carbons. So then how many missing bonds are there to that carbon? 3. So how many hydrogens are there? 3. Okay, so all of that is implied in this simple structure. So go ahead with the rest of the molecule and fill in where you think there are any missing hydrogens. Go ahead and take about 30 seconds to fill in the rest of that structure. And you can continue down to the rest of the molecules if you feel like you're on a roll. All right. Can I get a new volunteer to talk me through the other two carbons and how many hydrogens those have each? Kevin, can I ask you to volunteer? So you're saying the bottom right corner also has 3 hydrogens. Why is that the case? Nope. So careful. It's not about symmetry. It's not about balance. What is the rule that we're going to use to decide that this carbon has 3 hydrogens? So it ends up coming from the octet rule. Yes. And Sarah?
Carbon has to have 4 bonds.
Carbon has to have 4 bonds, which is based on the octet rule.
Okay.
So this carbon, we only see one line, one pair of electrons being shared. We know it has to have 3 more bonds to it. And because none of those are shown, they're hydrogens. If there's anything besides hydrogen, we have to show it. Okay? Sydney, what about this central carbon here? One what? Great, because there are already 3 bonds drawn to that carbon. 2 of them are to other carbons. 1 of them is to an oxygen. So there's 1 hydrogen missing and implied. All right, what about up here at the oxygen? Is there anything missing or implied at that oxygen? How many bonds does oxygen usually have?
2.
Usually has 2 bonds and 2 lone pairs. The more you see structures over and over again, you're going to notice that. So do we have that? What's shown? What's missing? Sydney, number 2. Need one more hydrogen. So luckily for us, if there is a hydrogen on anything but carbon, we have to show it. So how many bonds are there to that oxygen? There are 2. So that OH, the way it's written, is the same thing as saying this. So O and H next to each other implies that there's a bond. So it is a little bit of a shorthand, but it's not like we're missing whole atoms that exist. So we have 2 bonds to that oxygen. Is there anything else that we should put up there?
The 2 lone pairs.
And that is the entirety of all the implied content for that compound. Ready to step it up to aspirin? All right, I'm going to go ahead and clear the screen off. And then we're going to do the same thing for aspirin.
the general shape.
Oh, those are like double.
Alright, we have 10 responses. Make sure you hit send once you have your number figured out and entered. Are you in agreement or is there controversy?
Half a 9 to 10.
Do you have a worksheet? Grab one.
No, I grabbed one.
Slows you down. Scratch. That's why I give these to you. So you have something to start with. Does anyone need a worksheet? Anyone missing a worksheet? Alright, we have 17 responses. 20 more seconds. How much agreement is happening in this group? Yep. Okay. Does anyone want to draw on the tablet the missing hydrogens? Anyone? Cool. So it only registers the pencil, you don't need to worry about it. Okay.
Should I put the carbons as well or just the
If
hydrogen?
you want.
Okay.
Yes, go all out.
Okay.
So how do we feel about looking at a structure like this? Was it difficult to do the nitrogens on this one? Like to find how many nitrogens there were? Are there any implied nitrogens in this molecule?
Hold it.
So in the last one, there were no nitrogens because there was, you have to show them. You have to show anything besides carbon and hydrogen.
Should I do something about this?
So if we go around the molecule here, and this is terrible, I haven't remembered your name yet. I'm sorry. Tell me your name again.
Oh, I'm Taylor.
Taylor.
Mm-hmm.
So Taylor went around the structure, and she and her group decided that this is where all of the hydrogens were in the molecule. Is there anything that's missing or extra?
That's what I did.
Thank you, Taylor.
Thank you.
Okay, so she went around and she said, I see 3 lines to this carbon here. So that means it already has 3 bonds. It only needs 1 more, so there's only 1 hydrogen attached. She went around the circle and did the same thing. What about that carbon there? Should there be a hydrogen on that one? Nope. There's a double bond and 2 single bonds. There's already 4 bonds. That is full. Okay? And then what I really like is in addition, she went ahead and added lone pairs to the oxygen on the far left, the OH, and the oxygen on the far right, which is part of the amide. And we didn't even talk about it, but the nitrogen. Nitrogens typically have 1 lone pair and 3 bonds. She said, well, it's got 3 bonds, so it has 1 lone pair. So that's fantastic. So then what's our answer for the number of carbons, hydrogens, oxygens, and nitrogens? So, Taylor, can you read it to me?
Sure. How many are for each?
Yep.
I said 8 carbons, 9 hydrogens, 2 oxygens, and 1 nitrogen.
Does that sound about right? Okay, I didn't count it myself, so I'm going to trust you. Sounds good. Okay, so what this allows us to do is it takes a very, very huge amount of information and it puts it in the simplest possible format. So I am going to expect that going forward that you can read these. I might not force you to generate them very often, but you need to be able to look at it and say, based on what's there, I know what's implied and what's not. And then the next step is, where are the polar bonds? You all know how to do that? So I guess we can do it with the color scheme that we have on there. Go ahead on your drawing and circle any polar bond. You can do this in your group. How many bonds are you circling there? Careful, circle one at a time. Remember the O and the bond. They're sharing electrons. And then the O and the carbon are also sharing electrons. So those are 2 separate bonds. Did you have this from last time? Or maybe it was maybe a week and a half ago?
I think there were 6.
Yeah. There you go. So, can I have Gabby, Amber, and Jess discuss how you use this to answer the question of are there polar bonds? How many bonds do you circle right here? Which one? Okay. How many bonds are you circling here? So you're circling an atom, not a bond here, and then here you're circling a bond. So just be a little bit more specific. See the difference between what you two do? So think about, it's all about the 2 atoms' electronegativity. Are they close together or not? If not, then it's polar. Close together, it's not. That work? Say again. Yes, oxygen is not polar. It is irrelevant. You don't use that term to describe an atom. You use it to describe a bond. Yep. Okay. So when we're talking about polarity, the most critical thing is polarity only is something used to describe the sharing of electrons between 2 atoms. It has to be describing a bond. So if I went and I said, well, this oxygen is polar, that's gibberish. It's just like saying that a car speaks Chinese. Like, it's not something used to describe that type of situation. So instead of saying that that oxygen is polar, what would be a more appropriate term? The carbon-oxygen bond is polar because they're sharing electrons, but the oxygen is significantly more electronegative than the carbon. So we're comparing 2 atoms, and we're saying one of them pulls the electrons more towards itself, meaning that there is a partial negative charge at the oxygen because it has more of the electrons more of the time, meaning the carbon has to be a little bit deficient of electrons. It has a little bit fewer electrons than if it was equally shared. Are there any other polar bonds in this molecule? Michael, did you find any? Nitrogen to hydrogen bond. So if we look at the difference in electronegativity between those 2, we see this a relatively decent difference. It's 0.77. Is that right? So there's a pretty big difference in electronegativity between the nitrogen and the hydrogen that are bonded together. Any others? Taylor, did you find any?
Oxygen and hydrogen.
Oxygen and hydrogen in the OH. Great. Tina, did you find any?
I just circled oxygen. Yeah, oxygen to hydrogen. And then carbon to nitrogen.
So where is that? Is that on the left or the right side of the nitrogen?
On the left.
Okay. Anyone else? Sam?
Wouldn't it be a non or a polar bond between on both sides of the nitrogen and carbon?
I agree that both of those carbon-nitrogen bonds are polar because they're both defined by the same difference in electronegativity between carbon and nitrogen. Great. Are there any others that we've missed?
The other oxygen carbon
Where's that?
on the HO carbon.
So on the far left side of the molecule, there's a carbon bonded to an oxygen. So what are you noticing? What types of bonds are typically considered polar or have that unequal sharing of electrons? What are the ones that are most common? Say again? Hydrogen and carbon. Are they usually different or very similar? So let's talk about the ones first that are polar, and then we'll talk about the ones that are nonpolar. So which are the ones that are you repeatedly find are polar, that show up a lot?
Oxygen carbon.
Oxygen to carbon. Anything else to oxygen? Oxygen to hydrogen. And there are other ones, but not that we typically find in molecules. What else is usually polar? Bueller? Bueller?
Nitrogen carbon.
And? Okay. So a lot of students are taught in their biology classes, whenever you see oxygen, there's polarity. Wrong. Whenever there's oxygen bonded to anything but itself, there's a polar bond. It is not the oxygen that's polar, it is the bonding of the oxygen to something else that is less electronegative. So we're always going to look for oxygens in a molecule, because whenever we find them, they're not bonded to themselves. Polar bond. Same thing with nitrogen. If nitrogen is usually bonded to anything, it's usually hydrogen or carbon, polar. What are some of the other bonds that we see that we know automatically are not going to be polar? Anything bonded to itself, so self to self, I'm just going to say that's oxygen to oxygen, carbon to carbon, hydrogen to hydrogen, anything bonded to itself. Because by definition, we're always comparing two things, and if they have the same value of electronegativity, there's not going to be a difference. What else do we very typically see? So I'm going to highlight one. Carbon-carbon is the one that we see most frequently. Non-polar bond. What else do we very frequently see? Carbon, hydrogen. So this is the short list. If you memorize this list or just see it enough, you're going to save yourself so much time because you're going to look at a molecule like aspirin, and you're going to say, okay, I see an OH and OC on the far left side. We have two polar bonds there. That's an area of polarity of the molecule. In the middle, to the right side of the molecule, we have carbon, nitrogen, nitrogen, hydrogen, nitrogen, carbon, carbon, oxygen. That whole section is also relatively polar. One of the things to keep in mind, though, is everything that's polar the same polarity? What's the difference between, let's say, nitrogen and carbon versus oxygen and hydrogen? There you go. There's a bigger difference in electronegativity between OH versus CN. So if we have part of the molecule on the far left side of this molecule, we have two relatively polar bonds. On the right side, we have more bonds, but the relative difference in polarity is smaller because they don't have that OH, or there's not that big, strong difference. So when we talk about intermolecular forces, it's going to be really important that we think about not only are there polar bonds, but are there those really polar bonds? So we'll spend a bit of time with that here in the next few slides. But what I want you thinking about is on the back side of your diagram. I have a flow chart. It's kind of a crutch, but it helps us think about categorizing different ways that molecules interact with each other. And so for today, we're going to be talking about self interacting with self. So if I'm talking about aspirin, I'm going to say, how's aspirin going to interact with another aspirin? Or how's water interact with another water? We're not talking about making a solution, mixing different types of molecules together. That's what we're going to start on Wednesday. So this will be kind of simplified for now. Let's go back to those three compounds we talked about at the beginning of class. This is going to be the same type of, well, I use this a little bit differently. So I want to know, if we look at this molecule that I've shown here, which is pentane, does it have London dispersion forces? If it does, enter 1. Does it have dipole-dipole? If it does, also enter 2. If it has only 1 and 2, just enter 12, send. If it has 1 and 4, enter 14 and hit send. Does that make sense? So in theory, it could be 1, 2, 3, 4, send. But just make sure that it goes up in order of increasing number. So make sure the lower numbers first, and then only enter the numbers that apply for this molecule. What types of intermolecular forces? If you had a pure sample of lots and lots and lots of pentane.
If yes, then it is dipole-dipole. It also has H-related hydrogen bonds, and it is also so it can be. Yep. So this is the subset of this, the strongest subset. If you just say it only has dipole-dipole,
It means it doesn't have the strongest subset of it. That's a question. A lot of people miss that. Couple more seconds. Make sure you hit send after you put your numbers in. And closing out. All right, can I have a new volunteer to describe which ones of these you chose and the process? This goes a lot quicker if people volunteer. Taylor?
I picked one because it's a nonpolar molecule and it doesn't have any hydrogen bonding because there's no nitrogen, oxygen, or fluoride, and there's not an ion.
Okay, so we know it doesn't have an ion. That's super easy. How do we know it doesn't have these things? Okay, so one of the questions I got when I was walking around was, how do hydrogen bonds relate to dipole? And so if a molecule has a dipole in it, it has a polar bond in it, then we can say, well, is that one of the strongest dipoles, which we call hydrogen bonding? So for this molecule here, are there any polar bonds in this molecule?
No.
What are the only atoms that are bonded together in this molecule?
Carbon and hydrogen.
So we have a lot of carbon-carbon bonds all the way down that backbone, and then each one of these has a certain number of hydrogens in order to get to its full octet. So we could go around and draw out the entire molecule. But if we remember that table in the last slide, carbon, 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 hydrogen are always considered nonpolar, so we don't even bother with anything else. There are no dipoles, and if there are no dipoles, there can't be really strong dipoles for hydrogen bonding. So this idea of dispersion forces, it can be really strong if you have enough of them, but individually they're really weak. So like geckos stick to walls using dispersion forces, which is kind of crazy, but if there's enough surface interaction between things that don't have dipoles, you can create a little itty-bitty bit of a dipole because electrons repel each other, so you have this little back and forth between the two molecules, and the electrons get pushed back and forth. And that's enough to hold things off the ground. Pretty cool. All right, so let's take a look at the second molecule that we were working with. So go ahead and pick which ones apply For this molecule, if you had a pure sample of only 2 butanone, you had billions and billions and billions of these molecules next to each other. What are they capable of doing? Follow a little bit of what we're talking about? Are you available during office hours? Send me an email, let me know what times you would be available, and we could try doing like virtual office hours if you have questions and kind of identify areas that you can work on. This week is going to be rough for me because I'm actually traveling for a lot of it, but in general it should be something we can do. Okay.
What does hydrogen have to do with
I would go through the PowerPoint the day before.
Are you talking about getting credit for the right answer?
I'd have it all answered. Make sure I got those things right.
She's changed now. She no longer does credit for right answers. I want people to not stress about the answer. You're learning, right? You judges don't learn. All right, a couple more seconds to submit an answer.
So whenever you have like this oxygen out there, it always has 2 lone pairs.
It always,
Never implied to be almost always.
almost always, because every once in a while you see oxygen with 3 bonds, and then it only has 1 lone pair. It has a positive charge.
So it will when it's connected, when the oxygen like that is connected to the hydrogen, it will be stated, right?
Yes. All right, 25 answers. I'm going to go ahead and close out. So let's see what answers we have. We have a large majority of 1 and 2, but very few people are willing to stick their head out and say that it has hydrogen bonding. So how do we go ahead and decide it has London dispersion forces? Everything has London dispersion forces. If it has electrons around atoms, it has dispersion forces. Okay, and then we say, does it have dipole-dipole? How do we decide that? Are there any polar bonds? So to decide that, we then go in and we say, is there one of those bonds we say is always polar? We see that we have the oxygen and a carbon bonded to each other. So we have 1 polar bond. We look at the rest of the molecule. Are there any other polar bonds? Nope, there are none. So then we say, is there a really, really strong dipole where we could have a hydrogen bond? What has to be true in order for a molecule to be able to participate in hydrogen bonding? What has to be? Okay, so one of the biggest mistakes that people do is if I give them the same molecule but I put hydrogens all over the place, they say, there's hydrogens, it can participate in hydrogen bonding. What's wrong with that statement? In order for this hydrogen to participate in hydrogen bonding, it has to be part of a dipole. It has to be part of the strongest dipole. So only if you have an oxygen, fluorine, or nitrogen connected to a hydrogen do you end up with a dipole there. If you don't have this dipole, and that hydrogen is basically neutral, you can't have hydrogen bonding. So please never show hydrogen bonding just based off of the fact that there's a hydrogen. That is the most common mistake that people say when they're learning about intermolecular forces. If that hydrogen isn't very partially positive, it's not part of a dipole. So if you think about dipole has to be the qualifier before you can even consider to be hydrogen bonding, then that might help kind of filter that out. Okay? So we have a dipole, so if we had another one of these molecules, then we could say that we would probably have an arrangement something like this, and we would have an interaction between the partially negative oxygen in the dipole at the bottom with a partially positive carbon of the other molecule. That's the way that those 2 molecules are going to interact with each other. And to be a little bit more specific, it's not just between the 2 molecules, it's actually between the lone pair of 1, so the partially negative oxygen, it's between its lone pair and the partially positive next molecule. That's going to become important here in a second. Okay, so I concur with the majority of class. Do you ever go back in afterwards? I guess you can go in afterwards and you can look at the screen capture and the right answers. So I should probably go through and select the right answer so you can look at that afterwards. I usually don't do that, so I apologize. Seems like it'd be a useful study skill. All right, let's go ahead and talk the last one. We got an alcohol here, 1-butanol. All right, about 15 more seconds. All right, we're at 27 responses. All right, can I have a volunteer from our front table here to tell us what you decided that this molecule is capable of and why?
So we went with dispersion forces because those are always present. And since it is polar, there's dipole-dipole. And since there is a hydrogen bonded with an oxygen and other hydrogens attached to the carbons, there's also hydrogen bonding.
So I'm going to draw a few more of these, and I'm going to draw out that OH bond because sometimes it's easier if you have it drawn out. So Lauren said that we have polar bonds in this molecule. So we have one polar bond here, one polar bond here. Are both of those equally polar? One of them is a more polar bond. Which one is that? So the OH is significantly more polar than carbon-oxygen. So we have multiple dipoles in this molecule. Remember, there's multiple ways we can draw that. Maybe I'll draw the top one differently. So we can do delta plus, delta minus, delta plus. That those two molecules, the top one and the middle one, have the exact same information shown. One of them is showing that there's a partial positive and negative on different atoms. The other one's showing that the dipole, which represents the same thing. So if we have those molecules together, is there anything else I should add to those? So there are a lot of hydrogens on the carbons as well, but I want to see the lone pairs, because that becomes really important. So I love the fact that Lauren went through and she said everything has London dispersion forces. There are dipoles, and yes, we have the strongest possible dipole force there. So we have all three of these in those molecules. So if we were to say how many hydrogen bonds can each one butanol participate in? How would you answer that question? How many hydrogen bonds can each one butanol participate in? Talk to the people at your table. See if you can answer, or if you have any idea what I'm talking about. Alright, so let's do a finger vote. 1 hydrogen bond can participate in, 2, 3, 4, 5. Hold up number of fingers for how many hydrogen bonds you think it can participate in. Each molecule can participate in this many, exactly this many. What are we saying? Alright, does anyone want to argue their case? Who's confident wants to argue their case for how many hydrogen bonds can participate in? Michael.
You've got 2 lone pairs on the oxygen, which could connect to hydrogen and form more in addition to one over there.
Why wouldn't they already?
Okay, so Michael's point is kind of what I was referring to on the last compound, that in order to participate in a hydrogen bond, what do we need? What has to be on one side of the dipole-dipole interaction, and what has to be on the other side of it in a hydrogen bond example? So hydrogen has to be on one side, and what's special about that hydrogen? What are the only hydrogens that can participate in that? It has to be a really partially positive hydrogen. So it has to be bonded to something that's pulling its electrons away. So oxygen, nitrogen, or fluorine. You will never see, let's just get rid of fluorine. That's stupid. I don't know why they talk about fluorine. Because if there's HF, then you're going to die. And you don't want to work with HF ever unless you're in glass industry, and then they use that for etching glass. But it is toxic, super toxic. So it's just stupid. Okay. So you have a hydrogen that's very partially positive on one side. And then what has to be on the other side? There has to be a polar bond in what atom of a polar bond? It has to be partially negative, and it has to have a lone pair. So out here, we would have to have a partially positive hydrogen that's connected to an oxygen, nitrogen, or something else, right? So partially positive, significantly partially positive. Same thing right here. Or this could be, let's do that as a nitrogen, because that would work as well. And then at the top, what could we have that's interacting with that hydrogen? What would have to be there? What has to be in this box here?
Nitrogen, oxygen.
So if it's a nitrogen, it has to be a nitrogen with a lone pair. If we don't have a lone pair of nitrogen, we can't do it. So it has to be a nitrogen that's not attached to itself, an oxygen that's not attached to itself, or a fluorine that's not attached to itself. So it has to be partially negative, and it has to have a lone pair. So this is going to come into play here in one of the next questions I'm going to ask. Any questions on how we calculated how many hydrogen bonds each molecule can participate in? Okay. So let me have a right answer selected for that one. Okay, so now let's go ahead and see if we can apply this. Which of these molecules do you think will have a higher boiling point? Select your own answer first, discuss with your table. You can change your answer after you've discussed. You have to select your own first. these molecules can do dipole-dipole versus these ones can do dipole-dipole with strong hydrogen bond, you're going to have more attraction to it. So, yes, but it's all relative. Alright. Can I have someone from... Alright, go ahead. Can you explain what your group chose and why?
I don't know if it's right. You were contrary earlier. You talked about it. Okay. We chose A. Because there's a polar bond in formaldehyde, and it has more intermolecular forces to overcome before it can boil, so we picked that one.
So we noticed that both of them are almost the same weight, so that's irrelevant. So your group said that there's a big difference in how strongly attracted a pure sample of formaldehyde is from a pure sample of ethane. So if we look at the boiling point of those two, notice there's a pretty significant difference. It's about 60 degrees, almost 70 degrees Celsius difference between the two. So I agree, most of the class agrees with you. So I want you to be able to look at a molecule and to be able to decide, are there polar bonds? If there are polar bonds, can it also participate in hydrogen bonding? Can formaldehyde participate in hydrogen bonding?
Oh wait, it has lone pairs.
Oxygen has lone pairs, so we have half the equation. Then are there hydrogens that are very partially positive? Wah, wah. Those hydrogens are attached to carbons. Those hydrogens are nonpolar. So if you had formaldehyde with a formaldehyde with a formaldehyde, none of those have a partially positive hydrogen, and hence there's no hydrogen bonding possible. It is only capable of dipole-dipole, not dipole-dipole and hydrogen bond. Right? Because if you're saying that it does hydrogen bond, you're saying that this hydrogen or this hydrogen is very partially positive, but it's part of a nonpolar bond. So that's not possible. Samantha?
So when we're talking about like if it's possible for hydrogen bonding, does that mean like with molecules like it?
So I will try to be extremely explicit and give an example like this. If we have a pure sample of only this compound, can it participate in hydrogen bonding? So that's saying formaldehyde with formaldehyde. The other question that you're implying is, if we put formaldehyde in water, can that participate in a hydrogen bond? What's the answer to that? Yes. So,
the last one you just said that had the two extra coming off the lone pairs.
so what you'll see in proteins or DNA is that you'll see an amide. Let me do a blank screen here. So you'll see a nitrogen. So this is called an amide bond, a nitrogen with a hydrogen connected to a carbon double bond or to O. And there's a long chain of proteins that are connected with these amino acids that connect to make this long chain. But it ends up wrapping around itself multiple times. And so lower down there's going to be another one that's the same but maybe facing the other direction. And you can have a hydrogen bond between the lone pair of that lower oxygen and that extremely partially positive hydrogen on the other side. That is still called a hydrogen bond. So the definition of the hydrogen can't change. The hydrogen always has to be attached to nitrogen or oxygen. But the oxygen or nitrogen just has to be in a polar bond. It doesn't have to be in that most extreme polar bond. Does that blow your mind to not sit well?
No, I just still don't understand how the butane, whatever that one was, the one we did like before this one.
The butanol?
Yeah, the butanol. It had the two extra bonds coming off of the lone pairs on the oxygen, but this one can't.
So because this molecule can interact with another one of itself, very positive hydrogen, then those two molecules between them can form a hydrogen bond.
So because it already has hydrogen bonding, when it can like have those two others off the lone pair?
So if you're saying a pure sample, you have to look at it and say, anywhere in that molecule, is there an OH or an NH? If not, it's only dipole-dipole at most. If there is an O attached to an H, or H attached to an N, then you can say it should be able to participate also in dipole with hydrogen bonding in addition. Does anyone like or dislike the term hydrogen bonding? What's confusing about that term?
It's vague.
So one, it's vague because it just says hydrogen, right? And then what does bond imply?
Hydrogen is bonding to something?
So typically, in the most basic sense of the term, what does bonding mean? Sharing electrons, why? In order to form a covalent bond to fulfill the octet rule. Is that the case with hydrogen bonding? If you think about every example we've seen so far, and anyone you will ever see in your entire life, hydrogen bonding is not used to get to the octet. They already have octets. They have to. That's why you only have a partial positive and a partial negative charge. So I don't know if it's too late for me to go back to the earlier images I had. I don't know if I can. No, I can't get back to it. But you will. The most confusing thing biologists and chemists ever did was decide to call an interaction between two molecules bonding when you're not forming a bond. If you form a bond, you would actually have a covalent bond. You would have sharing of electrons to reach that octet, and you will never see that with hydrogen bonding. It is an intermolecular force. Here's one molecule of butanone or butanol. Here's another molecule of butanol. They're going to have some attraction to each other, but they're never going to be covalently bonded and form a new molecule that has new bonds in it from a hydrogen bond. Okay, so let's see if you're on point. How many total hydrogen bonds? That's weird. Totally spelled that wrong. How many hydrogen bonds can each ethylene glycol participate in? And this is talking about, for bonding it to another molecule and multiple molecules of itself, how many hydrogen bonds are possible in that molecule? So we're going to do 30 seconds more. We're going to get to 1 minute, and then we're closing this out. Try to save time by giving these instructions. 10 seconds. And we are closing out. Samuel, can you describe how you decided how many hydrogen bonds each ethylene glycol can participate in?
We looked at the previous, I forget the name of it, but the one that had just a single hydrogen-oxygen bond on the end, and we remembered that it could form three, and so we assumed that since it has both on both ends, that it could form three on each end or six in total.
Okay, great. Very good starting point. Does anyone want to dig in a little bit deeper into where those three are? So each lone pair of the oxygen can accept, is what that's called, accepting a hydrogen bond. So it has two places on each oxygen because they each have two lone pairs. By the way, there's an exception. Almost always when you see an oxygen, it has two lone pairs. The exception is hydronium, which hopefully is a polyatomic ion that you remember. That is hydronium. It's acidic water. So how many lone pairs does that oxygen have? Only one lone pair on that oxygen because it has, otherwise it would exceed the octet rule and we can't do that. Okay, so that's one of the few exceptions, but almost every other time, using Samuel's approach and saying we know just from pattern recognition that oxygen typically participates in two. Nathan pointed that out. Okay, and then where else do we have hydrogen bond capabilities?
The hydrogens themselves.
The significantly partially positive hydrogens that are attached to an oxygen, each one of those, and that's what we call hydrogen bond donor, is the partially positive hydrogen that's in a strong dipole. And the lone pairs, we call those acceptors. So this molecule has 4 hydrogen bond acceptors, the lone pairs, 2 hydrogen bond donors. And remember that there are no electrons exchanged, there are no covalent bonds formed in this type of bonding. Hydrogen intermolecular forcing, that's what we should call it, right? I hate the term hydrogen bonding. So it should be hydrogen intermolecular forcing, something much less smooth. Okay? So every single ethylene glycol can participate in 6 hydrogen bonds with something else. So then, what do y'all think about its relative boiling point compared to water? So it should be last question on the front side of the page, is that right? Question number 6, I think. Ten more seconds. Closing up. Can I get you to share your thoughts on what you answered and why?
I said higher because this one had 6 opportunities for hydrogen bonding, and then water has 4.
Great. So you have to think about what's the structure of water, how many hydrogen bonds can it participate in. So every water has 2 hydrogen bond accepting sites and 2 hydrogen bond donating sites. Here's what's kind of tricky about this. It's not only about how many polar bonds or how many dipoles there are, it's also about what percentage of the molecule can participate, what percentage cannot. In this case, you're right. So having 6 of the strongest dipole-dipole interactions does win out. Plus, it's also a little bit heavier, right? It has an extra 2 carbons and 4 hydrogens. So that is definitely a higher boiling point. We'll see some other examples where we need to think about both how much of the molecule is polar and how much is nonpolar, as well as what types of bonds those are. So the difference in boiling point of these is actually pretty significant. Ethylene glycol is 200 degrees Celsius. It's called antifreeze in the everyday world. So you add that to your car and it boils at a higher temperature. So if you're driving your car, this is what's flowing through the radiator in order to keep it from boiling off. If you just have water in your radiator, it boils off a lot lower temperature. For all those that spend a lot of time messing with their cars, probably have dealt with this. Or haven't had enough money to maintain their cars another time when this happens. All right. We're going to spend the last 5 or so minutes of class looking at a heat curve. Can you check at your table and make sure there's at least one person at your table who can remember what a heat curve is and what it represents? Talk really quickly. Make sure there's at least one person.
Yeah. So it's like how much energy it takes to get from one phase change to another, and then the energy.
Okay, is there anyone who does not have anyone with any clue? And Diana, me, or Umindra will come join you. Flags down. Okay. All right, so go ahead, and there's a couple questions after that. What are all the things that you can pick out there? And let's say that this is the heat curve for water. Pick out some specific temperatures. Pick out what the phase is at different points. Pick out what's happening with the molecules. And think about the transition. So take 5 minutes to fill in as much information that's represented, that's hidden in that diagram as you can. Okay. So these heat curves talk about one particular substance. So you have a different one for ethanol, a different one for water, a different one for chloroform, whatever it is. So this is a pure water. It starts out at a specific temperature, down at A. They take that and then they add heat to it. So you can say time that you've added heat, or how much heat is added. That's what the x-axis is. And then as you add heat, as you expect, the temperature of the substance goes up. But it gets to a certain point, and you keep adding heat, and the temperature doesn't change at all. And then you get to a certain point, and then the heat starts going up again. The temperature of the object goes up.
So would that be the curve?
So the heating curve is this type of a diagram.
Okay.
So what, if this is representing water, what are the 2 points at which the heat stops changing the temperature of it and does something else instead? So there's this temperature here and this temperature here. What's special about those temperatures?
So when it changes states.
So what's the state that you started with? What's the state in the middle? What's the state you end with? And then what's happening in these flat parts?
Nothing.
Is that when it's actually changing?
So think about adding heat as you're adding energy. So what's that energy doing here? What's it doing here? What's it doing there? What's it doing there? What's it doing there? So talk amongst yourselves. I think you have enough info to start that discussion. And if you want to label specific temperatures on the axis, that kind of stuff too. Okay. So what about what the molecules are doing? Add some specific temperatures on there.
Oh, okay.
So can you label the y-axis instead of a point on the graph? So it looks like your groups put temperatures on there, but think about the temperatures. You have a scale on the y-axis. So where on that scale are the temperatures you're and then what can you infer about the interaction between the molecules that's happening? That was right there. So what's happening between the molecules at these different points? You're adding heat the whole time, right? What's happening to them as you're moving up the solid? What's changing about the interactions between those molecules? Yeah, so try to include just some notes about that here on the diagram. So think about why heat is going in and the temperature is changing. And then all of a sudden it doesn't. Right? The temperature doesn't change at all right there. So think about what's happening with those molecules. Let's kind of go through the whole graph like that. Okay, we make some progress on this? Remember the underlying principles for this whole week and a half of class is think about the molecules, the properties the molecules have, why they're doing what they're doing. So if we start out at the very bottom, going from point A to point B, we start with a substance. What state is that substance in when we start? Okay, so it's a solid in that line between A and B. What are the molecules doing in a solid? How are they interacting with each other? So the motion of each one is a vibration, and how are they interacting with the other molecules around them? They're vibrating next to each other. Are they interacting with each other or no? They're really close to one another. They're in a very organized form, and they're not sliding past each other because they're going so slow that they're attracted to each other, and those attractions, those hydrogen bonds, are keeping them kind of locked next to each other because it's like little magnets with very little motion. If you start moving them around a lot, those magnets aren't enough to hold them in place. That's what I think of intermolecular forces like. But then you get to point B. What happens here at point B? The temperature stops going up, but you're still adding heat. The whole time you're heating the sample up. So what's happening? Sydney? Say again? So you have a phase change here. So what's happening with those molecules interacting with each other? So this is one of the terrifying things about the term hydrogen bonding, is that we say the bonds break. It's the right term that we've learned throughout our lives. Those hydrogen bonds, those interactions between the molecules are now being overcome. That those magnetic type interactions are no longer fast enough, or strong enough to hold the vibrations those molecules have, and they start sliding past each other. So I would love to use the term disrupt the intermolecular forces instead of breaking them, because breaking, once again, goes back to the idea of the octet rule. And we're not breaking octets, we're not breaking bonds. So all of that heat now goes into making them start to slide past each other, and we don't change the temperature of that solid. So that solid goes from, on the left side, it's fully solid. In the middle, it's a mixture of solid and liquid. And the far right side, it's all liquid. So by the time we heat it up to this point C, we're all liquid, but it's still at what temperature? So on our axes, we can put 0 degrees Celsius right there. And then we're going to heat it up. So we have a liquid, we're heating it up, heating it up, heating it up, heating it up, and the temperature keeps, the heat added goes to temperature change. And then we get to point D, and now those molecules are moving so quickly past each other that some of them start to escape. And then if we hold to that temperature for long enough, we're going to have another phase change. And on that far side, we're at a gas. Okay, so I'm kind of filling in a lot of the parts you had there. So the type of exam question I would ask with this would be, describe what's happening between the molecules in this part of the graph as you're adding heat. or cooling it down. We can talk about the opposite direction as well. If you don't have a good visual of what's happening between those molecules at different points in this type of a graph or this type of a situation, then that's something I want you to work on. That's something I want you to reflect on and identify. So what we're going to be starting to talk about in class on Wednesday is that this is how a pure sample reacts. What happens now when we take something and add it to that? We're going to add sugar, or we're going to add a salt to it. First question is, will it dissolve? If it doesn't dissolve and it's a stick of iron and we throw it in water, nothing is going to change about the water. So first it has to dissolve, which means like dissolves like. It has to be polar to dissolve in polar. It has to be nonpolar to dissolve in nonpolar. And the second thing is, if it does dissolve, how many particles are there? What's the ratio of particles? And based off the ratio of particles, it'll change the boiling point and the freezing point. So the primer for Wednesday's class has you specifically trying to deal with that, and it's going to have you do the calculations a little bit ahead of time, just so you're in the right mindset. But don't be scared too much about the calculations. As you know, my big thing in this class is to make you figure out some of the equations and stuff before you get to class. You don't need to worry about knowing how to use them too well. We're going to work on that in class on Wednesday. So I will set that up for you, and Ms. Katoum will be directing class on Wednesday. So be nice to her. I'll be out of town. So if you need anything from me, feel free to email me. But Ms. Katoum will be running class on Wednesday. She will be using eye clickers, and she'll be doing something very similar to this.
So did you say that you would